This is the introduction to the basic concepts of heat transfer and serves to remind us of the concepts we learned previously in the COP 311 module. First off, we will go over the link between thermodynamics and heat transfer. We will look at how we distinguish between thermal energy and other forms of energy, and also at the differences between heat transfer and other forms of energy transfer. We'll also apply this knowledge to perform general energy balances as well as surface energy balances when we tackle the tutorial problems for this section. Now, of course, the concepts of conduction, convection, and radiation will be revisited again just to refresh us. And these are in terms of Newton's law of cooling, Fourier's law of heat transfer, and the Boltzmann law, or the Seven-Boltzmann law of heat via radiation. Okay, so heat transfer via radiation. This knowledge will also be used to identify mechanisms of heat transfer that occur simultaneously, which we will discover in the tutorials and in later sections of heat transfer. And also develop an awareness of the cost associated with heat losses, which will be done at a later stage, and then we will end off with solving various types of heat transfer problems encountered in practice. Now, in your second year, you were introduced to the concepts of thermodynamics, which related the quanta of energy associated with states that were at equilibrium. For chemical engineering purposes, we often are more interested in the rates at which energy is being transferred for non-equilibrium states. For example, when you have a flow of fluid through a pipe and you have a constant rate of energy being transferred to that fluid. In this instance, we are talking about a non-equilibrium state. So let's get started and learn more about the concept of heat transfer. Now, heat transfer always involves a difference in physical properties. For instance, the physical properties can relate to a liquid, a gas, or a solid, but also the physical property can relate directly to temperature. And we've discussed this before. We've looked at the question of what is temperature. So I recall from COP that we were using this example of the thermometer and we were looking at the kinetic energy. So for example, if we stick this device, this thermometer, into some matter, we will end up with being able to read off a temperature from the thermometer. So this will work as follows. The thermometer contains some fluid, such as ethanol, maybe dyed red or blue, and the fluid is contained in a larger volume at the base of the thermometer, and then there's a very, very small volume that is made up of a capillary that runs across the height of the thermometer, or the neck of the thermometer. Now, when the volume is very small for the ethanol, the fluid inside the thermometer, as shown here, we perceive the temperature to be proportionally low based on this volume. When we stick the thermometer into something quite hot like lava, the fluid inside the thermometer would rise considerably before shattering from the immense heat due to thermal expansion. We associate this increase in volume with a proportional increase in the temperature. If we were to submerge this thermometer into something very cold like the Arctic Ocean, then the small volume associated with this low temperature would be read off on the thermometer. So all of this occurs due to energy being transferred in the form of heat to the thermometer. And we know that this transfer relates to an increase in the volume, and that this increase is due to the increase in kinetic energy of the particles that make up this fluid in question. In essence, heat is just one of many forms that energy can take on, and it is helpful to understand what other forms of energy can be manifested as. So in summary, let's have a look. We can talk about things like thermal energy, mechanical energy, kinetic energy, potential energy, electrical energy, magnetic energy, chemical energy, nuclear energy, etc. The total energy of a system tends to be the sum of all these energies that are present for the system, whereas the internal energy is specific to the microscopic forms of energy, which we cannot see. And this is a distinction that was made in the second year in the textbook Smith, Van Ness and Abbott, if you will remember that. So for instance, internal energy can be the sum of the kinetic and potential energies of all the particles or molecules within the system. Now, we're not talking about kinetic energy at the macro scale where we see a flow of a fluid through a pipe. We're talking about the internal kinetic energy of the particles themselves and also the potential energy. So kinetic energy is the energy that is associated with the molecule motion within the system, the molecular motion, right? It is also sensible in that it can be measured analytically using a thermometer or a pressure gauge, etc., and can be deduced by looking at other properties such as phase changes and also considering something like latent heat. How much energy have we put in order to change a physical property? So it's not just sensible like temperature, it's also latent. So latent heat, on the other hand, is much more difficult to measure compared to something like kinetic energy, which can be measured as a temperature change. Latent energy is more associated with a change in phase. So we can see this, but we won't be able to use a thermometer. A thermometer wouldn't register the presence of latent heat transfer, but we can still observe a change in phase, and transfer of energy, for example, may be measured by some other way. How many watt have we added to the system? How much watt have we added to our kettle to get it to boil off half of the amount of water that was contained within it. Boiling is an example of a phase change, obviously, and we can measure this indirectly, right? So those are the differences. Now, let's consider or take a closer look at what do we mean by internal energy. What is internal energy? We can write down a mathematical equation to describe what we mean. Internal energy is difficult to deduce except for changes of some microscopic concept or physical change. So the change in internal energy of a system would be equated to the sum of the change in heat that is taken up by the particles of the system and the change in work done on the system onto its surroundings. I'm using the plus sign here for dW in accordance with IUPAC and also Smith, Van Ness and Abbott. Sometimes the textbook likes to swap this around and say that it's work done by the system. Whatever your preference is, you can stick to it, but don't confuse yourself. Right. Now, we measure changes in internal energy indirectly by making measurements of work being performed and heat being transferred. But it's also, important to kind of have a look at some examples. What do we mean by internal energy? Can we use an example to explain ourselves? So have a look at these two examples and decide on whether or not they make good examples for the case of internal energy. So on the top right, we have a car that is moving along. It is therefore considered to have a kinetic energy that we can observe. Okay, so it's moving along in space. And on the bottom right hand side, we've got a mechanical clock. And within the mechanical clock, we've got all bits of moving parts. Some parts aren't really moving that we can actually see it. We have to maybe look at a very long time, and then we'll be able to see a spring that is tightly wound at first, becoming less and less wound up as time progresses. So, which do you think is a better example of internal energy? You can maybe pause here and give it some thought, and then move on. So, the first example, the car moving. This is not really a good example of internal energy. Why would you think this is the case? What makes this a bad example? Well, if you look at the collection of little bits and pieces that make up the mechanical clock, why do you think this is a good example of internal energy? Well, in general, internal energy deals with the molecules themselves, the internal constructs of the system. Where the car, we see the kinetic energy moving the car along from some reference point, where the internal energy of the mechanical clock changes irrespective of our reference point, how we're looking at it. All right. So, we can sum up the Q term, for example, in its mathematical definition and say, well, this is the inherent kinetic energy changes. And then we can also say, well, the potential energy change of the molecules related to each other is summed up by the work in terms of the mathematical equation that we use to describe internal energy. It's also often helpful to consider the difference between internal energy and what we have been introduced to in the second year, known as enthalpy. Enthalpy is related to internal energy, but it also includes changes for the system as it relates to pressure and volume. This is captured by the addition of the PV term. Okay, so this can be the change in pressure or the change in volume or both. And this is the main difference in internal energy and enthalpy. What, for example, would be the enthalpy for a group of hydrogen molecules? Let's say that these molecules are in space, and we mean space, a deep vacuum, no other thing around the hydrogen molecules other than themselves. Well, let's consider that there is no external pressure, therefore, because there are no other molecules. Okay, so there's no action, a pressure acting on the system. In this case, the enthalpy would equate the internal energy of the system. All right, so, what is enthalpy measuring exactly then? Well, enthalpy is only equal to internal energy if there's no change in volume or pressure for the system in question, of course. But generally, there are changes in pressure and volume here on Earth that arise due to the presence of molecules that make up our surroundings, such as air. The system would therefore push back onto its surroundings such that changes in volumes and or pressure would arise. So, in essence, enthalpy relates to both the internal energy and the external energy of a system, whereas internal energy relates to, well, just the internal energy within the system. One distinction that we can make is how we would typically measure each type of energy. So, for example, for enthalpy, we would make our analysis based on an external reference point and consider the macroscopic rather than the microscopic position, as well as the movement of the fluid as a whole. And remember, when a fluid is moving, it is due to differences in pressure, for example. All right. Well, internal energy, for instance, would be measured from within the system itself, where only the microscopic storage and dissipation of energy is considered. And you can think of Joule's experiment where he did work on a fluid, and that fluid took up the work, it heated up, and then over time dissipated this internal energy. So the energy was captured by the molecules, the molecules stored the energy, and then the molecules liberated the energy back to the surroundings. For example, if we added work to the system and its kinetic motion increased, and later this energy dissipated as heat, this energy is said to have been contained within the macroscopic constructs of the system. So this is a discussion of the internal energy of the system. Right, another property that we tend to often deal with as chemical engineers is that of heat capacity, or the specific heat of substances. It is helpful to understand how this property is measured in order to understand what it refers to. And I like to do this with other physical properties such as viscosity. It helps me to remember what these properties or physical properties refer to. So if we consider a quantity of energy that is supplied to a specific amount of mass, we can measure by how much the substance will heat up. So for example, if we have 1 kilogram of liquid water, so that we heat it up and its temperature increases from 24 degrees to 25 degrees, we will require a total amount of 4.18 kilojoule of energy in order to heat up this 1 kilogram of liquid to 25 degrees from 24 degrees. So another way of looking at this property is how much energy is required to change a 1 kilogram substance's temperature by 1 unit. Okay. So note that we can add this quantity of energy to a system that is either at constant pressure or at constant volume. And for gases, this will matter a lot. Usually Cp is much greater than Cv, but obviously it depends on the substance. But in general, Cp is always going to be greater than Cv. Okay. Now, at constant volume, let's consider what happens. At constant volume, the internal pressure of the system would increase with the addition of heat, thus increasing the system's internal energy. For a system at constant pressure, the energy density of the system would remain the same and thus relates more to enthalpy. But obviously then there would be an increase in the volume for the system. Obviously work has to be done on the surroundings in order to increase the volume and maintain the pressure. So this is the reason why Cp, the specific heat at constant pressure, tends to be larger than Cv, okay, because work has to be done in order to overcome the volume, the volume that is being displaced by the surrounding matter. Okay. Now, solids very rarely show changes in their volumes when you add heat to them or you transfer heat to them. So therefore, the heat capacities generally remain the same irrespective of any volumetric or pressure considerations. So we say that Cv is equal to Cp and that the specific heat is only a function of temperature for solids. Right, so if we look at something like an incompressible substance, a fluid like water, where density would typically remain constant, then in this case, and also for the case of real gases that can be treated as ideal, the Cv and the Cp depend only on the temperature in question. Okay, but these two values, Cv and Cp, obviously will be different, but they only depend on temperature, similar to the solids. Okay, so that's a nice simplification to keep in mind. Now, heat transfer can be considered in various ways. For instance, we can talk about heat being transferred as an amount of joule. Okay, so 1 kilojoule, 1 megajoule transferred to the substance. Or we can also consider how quickly or how slowly do we take this quantity of energy, 1 kilojoule, 1 megajoule, and transfer this per time. And in essence, we end up with another measurement called watt, joule per second. And lastly, we can also consider the heat flux, which is the rate of energy transferred per unit area, especially in the case of heat exchange equipment, because we designed this equipment to have a certain amount of area through which we want heat to be transferred. Okay, so all of these concepts are important. Now, recall that the energy within a system, whether accumulated or diminished, is the difference between the energy into the system and the energy out of the system. So it's the net efflux of energy through the system. So in other words, the energy accumulated or diminished within the system is equal to the heat that is being transferred into or out of the system. And so just remember this when you have to do an energy balance across a unit operation, etc. You'll need to just remember your first and second year work on energy balances. So don't forget about that. Next, let us consider differences for this concept. Okay, so when we apply this concept, or the energy balance applied to a closed and an open system, what are the differences? So for a closed system, the unit of measurement would be joule. Okay, whereas for a moving system, where the fluid is constantly moving, we would want to add a certain energy per time, so joule per second, to each unit of fluid that passes by. So instead, we would want to make use of watt. Okay, this would make more sense and is more applicable to us chemical engineers, because oftentimes we have fluids that are moving through piping systems, etc. Okay, so closed systems are very rarely something that we deal with as engineers. They're very easy because they are at equilibrium, whereas with moving fluids, there's constant dynamics at play. And so it is more useful for us to develop our understanding around this joule per second transfer of energy. Right, now, mathematically, we should all be familiar now with the following equations, because we learned about them in COP. Heat transfer can be explained, for example, by Fourier's law of heat transfer or via conduction. Newton's law for heat transfer, which is called Newton's law of cooling, okay, which relates to the convection or the motion of fluids. And then Stefan Boltzmann law of radiation, which relates to energy being transferred due to electrons becoming excited and then dropping back down to the ground state and releasing a radiation in the form of photons, pockets of photons or packets of photons. Okay, photonic wave, okay, electromagnetic radiation. Let's consider conduction first. So again, the principle of conduction refers to the energy that's transferred through physical contact between substances. These can be solids, they can also be liquids or gases, okay? And typically then the liquid and the gas would be more or less stationary, right? Remember, particles are always in motion, even in solids, but there isn't a bulk motion in this case when we consider conduction only. Okay, so conduction neglects any motion that would otherwise assist energy transfer. Okay, so we've spoken about the driving force of conduction. This is the temperature difference, while the thermal conductivity tells us how easily or how difficult energy is transferred through a substance. Okay, so gold would have an easy time, whereas air would have a very, very difficult time, irrespective of what the temperature difference is. So, irrespective of how large the temperature difference is, if a substance has a very low thermal conductivity, it would resist conducting energy through itself and inhibit energy being transferred. Therefore, we need to consider all terms to decide on how much energy would be transferred, including area, as we see in this equation. We can consider an analogy for this. So, for example, dt is likened to that of a slope of a hill, while Q is maybe a whole lot of vehicles that are stuck in traffic on top of the hill. K would then be the friction, it would also be the number of potholes, it would be the braking systems, how sharply cars are braking and causing other cars to brake, while the area is maybe the number of lanes available for the cars to travel along. Thermal conductivity is a property of a substance, and so it can change. It's typically also a function of temperature. But the type of substance and the phase of substance really does make a huge difference. So since conduction relies on contact, solids or the particles present in solids tend to have a higher thermal conductivity since the molecules themselves are much closer together, so they bump and collide into each other much more readily. Gases are opposites, they tend to have lower thermal conductivities, okay, since their molecules are furthest away from each other. And obviously I mentioned temperature. Temperature can affect thermal conductivity significantly if the temperature range is considerable, right? If it is wide enough. So for example, look at the very small variance in thermal conductivity for gold, silver, and copper between a temperature range of 200 Kelvin and 300 Kelvin. It's really insignificant, and therefore we would often, consider treating conductivities for solids in this case as constant, because we don't often have very large temperature differences, even in chemical engineering practice. And this also has to do with the fact that certain substances can undergo thermal shock if too higher differences in temperatures. Okay, and also we don't like to have phase change within pipes and heat transfer equipment because these are much more difficult to model, design, and operate and control in the end. Right. An important property to remember when dealing with heat transfer, specifically thermal conductivity, but also convection, is the thermal diffusivity. So we've come across this property before, and it relates to heat being transferred via conduction. And so the heat being transferred is looked at versus the heat being stored by the substance. And this is equal to the thermal conductivity divided by the density multiplied by its heat capacity. Okay, so what are the units for thermal diffusivity? Quickly figure them out and decide for yourself which other physical properties of substances have similar units or the same units. Right. Now, a substance like gold, for instance, would typically have a very high thermal diffusivity because it has very high thermal conductivity, so it would conduct a lot of heat compared to its relative density and heat capacity, while something like alcohol would have a very poor thermal diffusivity because it tends to store a lot of the energy. Okay, so it doesn't transfer heat that readily, and so thermal diffusivity can tell us how readily heat is being conducted versus how much heat is being stored up in substances. Next up, let's quickly have a look at convection in summary. So convection differs from conduction in that energy transfer relies on the motion of the fluid, so that heat is moved away by this motion from one locality or one location to another. Recall that the rate of energy transfer by this mechanism may be increased by increasing the motion of the fluid in question. So, as an example, you can try this at home if you have the time and an egg. Yeah, I have ducks. I have many eggs. So many eggs. Any case, Similar to conduction, the driving force for convection is the temperature gradient, while the vehicle for transfer is the convective heat transfer coefficient, H. And realize here that H depends on the motion of the fluid. So in the table shown, as you can see, an increase in the fluid motion typically would increase the convective heat transfer coefficient. And lastly, we have heat transfer via radiation. One thing that you should always keep in mind is that the Stefan Boltzmann constant is very, very small. Okay, but also that the temperature here in this case is to the power of 4. So these are, two juxtaposed quantities. One is very small and one will tend to be very large. So therefore, unless the temperature is high enough, radiation would not typically be considerable compared to the other mechanisms in question. Okay, and you should really try to get a feel for when radiation is negligible and when it becomes something that is considerable. Okay, so when dealing with radiation, we'd often consider it within different systems. So there are two opposing systems shown here. Okay, that are present. So if this is the case, we would then consider the net energy that is being transferred between the two systems. Okay, so you would have maybe a hot iron radiating off into a cold room. And so the net radiation in this case would be considered, where the temperature would be in Kelvin. So remember the units for this. Okay. It is also very likely that this form of heat transfer is not efficient. Okay, so this is due to the ability of matter to emit energy or reflect energy away from itself. And it's also based on the ability of different substances to absorb energy. So for example, copper, I think, has an absorptivity of, was it 93%? And something very black would be 95 to 98%. And something white would be very low. Okay, so we often want to factor in emissivity as well as absorptivity when we consider radiation. Okay, so keep this in mind and consider how you would use these two principles. Okay, so if I give you information on absorptivity, would you be able to determine emissivity? Okay, so these two concepts, emissivity and absorptivity, are related to each other, where emissivity equals 1 minus absorptivity. Okay, right, now to end off the lecture, let's go over a few examples. So consider the following. Which is the driving force of A, heat transfer, B, electric current flow, and C, fluid flow? You may pause now and then quickly write down your answers and then move on. So firstly, we know that temperature is the driving force for heat transfer. Voltage is the driving force for electric current flow. And pressure, or differences in pressure, is the driving force for fluid flow. Next, what is heat flux and how does this relate to energy transfer? First, consider your answers. Maybe think about a mathematical way of relating these two entities, and then move on and let's consider answering the solution. Okay, so of course the main differences here relates to the area through which heat is being transferred per unit time, and you can use these two equations to relate these two quanta with each other. Okay, next up, how are heat, internal energy, and thermal energy related to each other? So give this one some good thought before moving on. Okay, firstly, thermal energy relates to both the sensible and latent forms of internal energy. And thermal energy is also referred to, as heat, often in our daily lives. But thermal energy is is both sensible and latent forms of internal energy. All right, so always remember that. Now, next, consider the following question. Let's say we have an ideal gas. It is heated from 50 degrees Celsius to 80 degrees Celsius at a constant volume and a constant pressure. Which case do you think more energy would have to be transferred, and why? Heat under constant pressure requires more energy, since Cp is always greater than Cv, but this is also because work is required to keep the system at a constant pressure, and so that's why Cp happens to be greater than Cv. Say you have two identical rooms, where one room has a fridge inside of it while the other does not. If all the doors and windows are closed, while the room that contains the refrigerator is cooler, I mean, will the room that contains the refrigerator be cooler or warmer than the other room? Okay, so all the doors and windows are closed. One of the rooms has a fridge and the other one does not. So consider which room would be warmer, and what would happen in this case if the refrigerator door or doors, so both the freezer and the fridge doors, were left open. And consider, your answers. Why would you give these answers? And maybe pause before moving on. Okay, so for the first question, will the room that contains the fridge be cooler or warmer? The answer is that this room would be warmer. The reason is because electric work has to be supplied to the refrigerator all the time, okay, to keep it cool. And this work is dissipated eventually as waste heat. And so the fridge that, the room that has the fridge will always be warmer. It's irrelevant whether the fridge doors are left open or closed, because on average, the room that contains the fridge will receive electrical work, and so overall it will be receiving waste heat. Okay, question 6 asks, a 2 kilowatt electric resistance heater is in a room. It is turned on and it is kept on for 50 minutes. The amount of energy transferred to the room by the heat is option A, B, C, D, or E. Quickly do the calculation and then move on. The answer should be 6,000 kilowatt or 6 megawatt. So that's a fair amount of energy there. Okay. Consider a 2 kilowatt electric heater, and this time it's submerged in 30 kilogram of water. The Cp value for water is 4.184. We consider water to be incompressible, and so we will consider only the Cp value in this case. Okay, this electric heater is kept on for 10 minutes. So during the process, we measure that 500 kilowatt of heat is lost from the water. What is the temperature rise of the water? Is it A, B, C, D, or E? Quickly pause and give it a go. The answer is A, 5.6 degrees Celsius. If you did not get this, just consider the energy balance again. You have 2 kilowatt. It's been turned on for 10 minutes. And you also have a 5 kilowatt loss of energy over this time. See if you can get the answer. This ends our lecture on the introduction for heat transfer. I hope to see you guys soon.